Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is July 5th, 2017. The title of this lecture is AC/RLC Parallel Electrical Circuit Analysis. In this lecture you will learn how to calculate the variables involved in an alternating current resistor-inductor-capacitor RLC parallel AC electrical circuit. The typical AC electrical circuit consists of control systems which regulate both current and voltage using individually oscillating and alternating voltage and current sine waves as depicted below in this drawing here. Now let's calculate the data below for the given AC parallel RLC electrical circuit. This circuit has an RMS, or root mean square effective voltage, of 220 volts AC, operating at 60 cycles per second or 60 hertz. It has a parallel resistor resistance integrated into the circuit of 775 ohms, an inductor in parallel as well, measured at 1.75 henries of inductance, and as well as a capacitor with capacitance measured at 18.5 microfarads of capacitance. These are the values here that must be calculated or known in order to understand the characteristics of this given circuit. So starting with what we do know, total RMS voltage for the circuit, 220 volts RMS AC. The circuit frequency, 60 cycles per second or 60 hertz. A total resistance of 775 ohms. Total inductance, 1.75 henries. Total capacitance, 18.5 microfarads. Micro implies 1 over 1 million, or 1 millionth. So 18.5 divided by 1 million yields a whole value capacitance of 1.85 times 10 to the 1, 2, 3, 4, negative 5 power whole farads of total capacitance. So we have to start with calculating the inductive reactance X sub L. So we simply calculate the angular frequency, or 2 times pi times the circuit frequency times the whole value of inductance in henries, which is 1.75 henries. So when we do so, we calculate an inductive reactance X sub L of 659.7 ohms. Next we have to calculate the capacitive reactance X sub C, which is the angular frequency again times the whole value of capacitance in farads, which would be this value. This whole quantity, when multiplied, you take the inverse of it, or the reciprocal value, and that will yield the capacitive reactance X sub C. So after doing these two, we move on to calculating the current at the resistor. And remember, in a parallel circuit the voltage is constant, whereas the current fluctuates and is not constant. Whereas the series circuit, the current is constant and the voltage can fluctuate or have drops. But this is a parallel circuit, so that means the voltage is constant. So we have to focus at the on the current at the resistor, inductor, and capacitor. So I sub R, the current at the resistor, would be equal to the total RMS voltage divided by the resistance of the resistor. So 0.28 amps at the resistor. Next, the current at the inductor is also the total voltage, but this time divided into the inductive reactance. So instead of dividing it into the resistance of the resistor, we take the total voltage and divide it by the inductive reactance, because it's an inductor. And when we do so, 220 divided into 659.7 inductive 659.7 ohms inductive reactance. So when we divide these out, 0.33 amps is the current at the inductor. then we calculate the current at the capacitor, which is the total RMS voltage divided by the inductive capacitance. I'm sorry, the capacitive reactance. It does get kind of confusing on the wording, but the capacitive reactance. X is always the reactance, and then the sub value is either capacitive or inductive, so capacitive reactance. So when we divide these out, 220 divided into 143.4, 1.53 amps current at the capacitor. So now we got all three current values at all three resistor, inductor, and capacitor components. Next we have to calculate the impedance for an AC parallel RLC circuit, which is different from the AC series RLC circuit. So we abbreviate it with Z sub P for parallel, and it would be represented by this formula here. So the easiest way to do this is just take 1 over the capacitive reactance, and then hold that, whatever you get there, hold that, and then take 1 over the inductive reactance, and then subtract these two values, and then whatever you get, square it, and then hold that value there, and then move on to the other side and just take 1 over the resistance in ohms at the resistor, and then whatever you get there, that value, square it, and then get the square root of that, hold that value, and then take 1 over this value. And now you have two separate values you can simply add, and when you do so, you get 178.3 ohms of parallel AC circuit impedance on an RLC circuit. With that value, we can now calculate the reactive current, which is applicable to the AC parallel RLC circuit. So that's simply just the difference between the current at the inductor from the current at the capacitor. So 0.33 minus 1.53, we have a reactive current of negative 1.2 amps. So if you graph this formula on a graph, it would actually imply that you're going to have a greater current at the capacitor versus the inductor. So you're not going to see the inductive or capacitive nature on this type of a circuit, but you could, if you broke down this numeric value graphically, you would see that it's leaning towards a greater current at the capacitor. But we can also compare that numerically too, that we have a greater current at the capacitor compared to the inductor, and you'll know why that's important in a little bit. So next we have to calculate the total current, the total RMS voltage divided into the circuit's impedance. So when we divide those out, 1.23 amps applicable to the AC parallel RLC circuit. And we already mentioned that voltage is constant in a parallel circuit, current is not. So therefore, the voltage drop across the resistor, inductor, and capacitor are all going to be equal to the total voltage in the circuit, 220 volts RMS AC voltage. Next, we move on to the power factor, which is a different formula for the AC parallel RLC circuit as opposed to the series AC series RLC circuit. So in this case, it is the current at the resistor, 0.28 amps, divided into the total current, 1.23 amps. You notice that is a ratio of current because the voltage is constant, whereas in the series AC RLC circuit, it is a ratio between voltage, because the voltage is constant in the parallel circuit, and the series circuit, the current is constant. So you have to use what is not constant. So it's 0.28 amps divided by 1.23 amps, so we have a power factor of 0.23. And next we calculate the apparent power for AC circuit, AC RLC circuit I meant, and that is simply the RMS voltage times the RMS current. So we have an apparent power for this given circuit of 220 volts RMS times 1.23 amps RMS, or 270.6 volt amps of apparent power. Now to calculate the true power AC, we would simply take the apparent power and multiply it times the power factor for the given circuit. That should actually be a little p for parallel. Let's see if yet. That was just a little typo, but it should be power factor PF sub P. So power factor sub P. Okay, now we simply just take the apparent power, which is the RMS voltage times the RMS current, and then multiply it times the power factor, all three. Then we get true power, AC wattage, AC true power in watts, not volt amps, but in watts, the actual power you get in this particular circuit setting, and spec 62.2 watts, the product of these three. Next, we calculate the phase angle, and like I said, going back to the introduction, the voltage and the current, well, if they're not in phase, they will either lead or lag each other by a certain amount of phase shift degrees or a phase angle. That's what that implies. So if we go back down here, the phase angle is equal to the inverse cosine of the power factor. So if we take, what did we calculate? 0.23. So if we take the inverse cosine of 0.23, that would equal 76.7 degrees phase angle. So now the last question, actually one of the most important questions culminating this data and calculation, is what is the relationship between the current and the voltage? Well, you first want to look at the capacitor, the current at the capacitor versus the current at the inductor, and the current at the capacitor is greater than the current at the inductor in this given circuit analysis. So that means the current will lead the voltage by a certain phase angle, in this case 76.7 degrees, because in an AC parallel RLC circuit, the current will lead the voltage when the current at the capacitor is greater than the current at the inductor. So go back and look at I sub C. I sub C, we have a current of 1.53 amps, which is greater than I sub L, 0.33. So what that implies is that the current will lead the voltage by a phase angle of the inverse cosine of the power factor, or 76.7 degrees, because in an AC parallel RLC circuit, the current will lead the voltage when the current at the capacitor is greater than the current at the inductor. Now, if the current at the inductor was greater than the capacitor, then the current will lag the voltage by a certain phase angle, and it would not be this value, because if the values were different at the inductor compared to the capacitor, compared to what they are, then we would get a different power factor, and then we would get a different phase angle. But what's important to understand is that when the current at the capacitor in an AC parallel RLC circuit is greater than the current at the inductor, the current will lead the voltage. If the current is greater at the inductor compared to the capacitor, then the current will lag the voltage. This is applicable to an AC parallel RLC circuit, because we're dealing with constant voltage, so we have to focus on the current difference. So that's how you answer one of the most important questions, calculating it mathematically and algebraically longhand here. So that completes this lecture. Thanks for watching, and have a great day.